Hello, this is the Acoustic Species Identification Project, and our team consists of Ludwig, Sean, Vibhuti, and Jilan. Today, we'll be discussing our research and findings in tackling the domain shift problem, specifically in classifying bird calls within very noisy soundscapes. We began with exploring different architectures to optimize audio classification and transitioning from traditional spectrograms to innovative models like Mamba. Now, let's have a look at the various methods used and the preliminary results achieved in our study.
One prong of our research was into updating the architecture for classification. So traditionally, audio is turned into a spectrogram, which is an image that is then fed to a convolutional network to classify it. But recently, these types of recurrent state space models have emerged as a potential to model audio directly and classify it without turning it into a spectrogram. So that was the original vision. And we used a combination of sashimi and Mamba architecture, which was not publicly implemented prior to this project. So it took some work, but we got adapted code working, but it ran very slowly compared to convolutional networks, on the order of 1 to 2 clips per second for sashimi or Mamba, to 180 clips per second for convolutional networks. So that meant we could train, but not long enough to produce reasonable comparisons. Thankfully, over the course of this project, another paper and another model came out that uses Mamba architecture on spectrograms, and it's pre-trained on a bunch of unsupervised data, which in theory should help it adapt better. Controlling for the number of clips seen, at this case, about 1.5 million. We see that it does adapt more quickly than convolutional nets. However, again, we couldn't train it as long as convnets because it could only process about 10 clips per second. So, the validation results are somewhat mixed, but it's encouraging that training performance is quite good. So spectrogram modeling is still the way to go, but maybe we can adapt more quickly with pre-trained models in the future when they're better optimized for hardware.
For our second prong of research, we explored new representations of audio data. As noted before, the standard approach to audio classification in this domain is to convert the audio waveform into a spectrogram, which is then treated as a natural image by a convolutional neural net. A standard CNN does this by iteratively scanning the image with small patches. However, this approach is meant to introduce the implicit bias that the meanings of objects and images tend to be spatially translation invariant. When applied to the audio domain, translation invariance along the two dimensions of the spectrogram means different things. In particular, translation invariance along the frequency domain means that we do not need to be sensitive to changes in absolute pitch. This is a suspect assumption, so instead we created a small residual net whose kernel looks at all frequencies at once in a small window of time and scans along the temporal dimension. So for our first question, we ask whether we can treat the spectrogram more naturally as a time series object rather than an image. The second question we asked was whether audio data could be easily disentangled to make training easier. This was inspired by work studying the neural architecture of flybrains. We compared the three models here: the standard approach, the modified CNN, and the modified CNN with additional feature disentanglement. It seems, however, at least under the Kaggle metric, that there is no benefit to using the experimental approaches.
Let's talk about our MVPD ensemble. We trained 9 different CNN models with 5 major architectures. Here we can see the results showing us that although 2 of our models timed out in the submission, we achieved a score of 0.66, which placed us at 91 out of 914, winning us a bronze medal in the competition. After some challenges we encountered because of Kaggle and the competition rules, we were able to improve our inference time using Onyx and ran one ensemble successfully which scored 0.59. Hence, we achieved our milestones for our MVP, the ensemble, and are currently looking into some further optimization techniques like using Rust plus Onyx. Here's a quick overview of the code on our Kaggle notebook showing how we first load our pre-trained models, convert the soundscapes to spectrograms, and then running the classification on the soundscapes. We use the existing acoustic multiclass pipeline to train each model while experimenting with different data documentation settings and other parameters.
In conclusion, our team has made significant strides in the fields of acoustic species identification. Despite facing challenges such as lower training speeds and generalization issues, we have successfully implemented various models and architectures. Moving forward, we aim to further refine our models and explore advanced techniques like Rust plus Onyx for improved inference times. Thank you.